A lot of you are looking for help getting a job in the chromatography world. You're going to find jobs available in the petroleum industry, in the pharmaceutical and biotech and environmental and every industry out there. And when you're preparing for an interview, these are the 12 questions that I think you should know the answers to. So the first thing the interviewer is going to want to assess is your basic knowledge of chromatography. So they may ask a question, what is the primary principle behind the techniques of HPLC and GC? Now the answer to that question is that these are separation tools, and what they do better than any tool in the world is they separate complex mixtures into pure compounds. We separate to identify, we separate to quantify, we separate to purify, but step one is to separate. But now let's talk about how that separation occurs. In both LC and GC, we have an affinity for the stationary phase. So in the GC world, we have a stationary phase and a mobile phase. Mobile phase is a gas, we're passing through the column. And the stationary phase is a place for the analytes to spend time. So in GC, the separation is based on mostly the boiling point of the analyte and how much it likes the stationary phase. That's it. In liquid chromatography, there's one more level. Not only is it the relative affinity for the analytes for the stationary phase, but it's the relative affinity for the stationary phase versus the mobile phase. So in LC, the molecules are given a choice. They can spend time in the stationary phase, they can spend time in the mobile phase. Each one has its own attraction. In GC, you basically have the stationary phase, things stick, and the mobile phase plays no role except to push things through the column. We start off with the injector, it's the auto sampler, and then the next part is the inlet, and then we have the column. So if I pop this open, we can see a column, and then I have the detector, and then ultimately the data system. So those are the components of the GC. Now the HPLC, we're going to have similar components. We start with the solvent bottles, we go through a degasser, we then move on to the pump. From the pump, we've pressurized the solvent, and we could go on to the auto sampler. That's where we're going to pick up the sample. From the auto sampler, we go to the column, and I'll pop this open. The column, in our case, is going to be a tiny little column that looks something like this. And then ultimately, coming off the column, we end up in the detector in order to see what we've separated. So those are the components of both the GC and the LC. You can see the similarities. Of course, if you want the deeper dive, check out the deep version of this on Axion Lite, and I'll give you the real details. So obviously, big question. There's a lot of different columns out there, but a simple answer is, in GC, there's one go-to column, and that's the DB5. And when I say DB5, it's RTX5, ZB5, depending on who you're buying your column from. But it's 5% phenyl, 95% methyl, piloxyloxane, and that is sort of the go-to column, good at most things. That's the one that we usually try first. In HPLC, again, it depends what the analyte is, what the matrix is, but I will give you the 85% answer, and that is 85% of the people in the world are going to choose a C18 column with either methanol water or acetonitrile water as the mobile phase. Not the answer for everybody, but it's going to get you pretty far when you're starting off from scratch. In GC, we have a dozen detectors, but there's one that dominates. It's the flame ionization detector, the FID. It dominates because it can see anything with carbon-hydrogen bonds, which is any organic material on the planet. So since most things we do in GC are organic, this is the perfect detector for most things. Great detection limits, part per million, subpart per million detection limits, and easy to use. So in the GC world, pretty simple answer. FID is the number one, the major detector. In the LC world, very analogous situation where we have one really common detector. It's called the UV visible detector. So UV vis, obviously by the name, it's shining UV and or visible light through the flow cell. And if the analytes can absorb that light, we will get a signal. So in the UV vis world, we have a bunch of different, what I call flavors of UV vis, but the most powerful of them is called the diode array, and essentially the way it works, we have a flow cell, a bright light, we shine light into the flow cell, and we measure how much light is absorbed by the molecules. So another thing the interviewer may want to know is, do you understand the separation? Remember, we've already established that chromatography is this separation tool. So how will the interviewer probe your knowledge of separation? One question might be, what's the cause of poor resolution in GC and in HPLC? Remember, GC and HPLC are separation tools. We need to resolve peaks. So if we have poor resolution, it means the peaks are stuck together. So the answer to this question is, there's three things that affect resolution. Only three things. We call them capacity factor, selectivity, and efficiency. But the bottom line is one of them must be bad, and we need to figure out which one it is. These are easy to measure. We can measure them, compare them with what they're supposed to be, and then correct the one that's wrong. The capacity factor, if it's too low, then it's almost always in the GC world, then your temperature is too high. The column temperature is too high. Lower your column temperature by 25 degrees, you will double your capacity factor. That is probably the biggest mistake people make. They set the temperatures too high, and it's reflected in a poor capacity factor. Selectivity tells us if you've chosen the right stationary phase, and efficiency tells us if you have the correct column dimensions. So that's the idea of what affects resolution in the GC world. Now in HPLC, it's going to be the same answer. Because in HPLC, just like GC, it's the exact same technique. We have the same resolution equation, which means there's still only three things that affect resolution in LC: capacity, selectivity, efficiency. Capacity factor in LC is all about solvent strength. So you need to weaken your mobile phase. If your capacity factor is too low, you weaken the mobile phase. What does that mean? Add 10% more water. I assume you're doing reverse phase like the rest of the world. You add 10% more water, and then that will dramatically improve capacity factor. That's going to be the biggest improvement in your resolution. Selectivity, more complicated. It says, do you have the right chemistries involved? And then efficiency, just like in GC, do you have the right column dimensions? Do you have the correct particle size and the column length? So retention time, very important in both chromatography, both LC and GC, and very simple. And that is, retention time is the number of minutes it takes a molecule to come off the column. It's measured from the point of injection to the apex of the peak. So when we start the injection, we start the stopwatch, we reset it to time 0, and we time how long it takes the apex of the peak, not the first molecule, but the average of all the molecules to come off. So the retention time is important because it's how we identify things. So retention times are characteristic, which means every time I inject caffeine on my HPLC under a set of conditions, it'll always come off at the same time. So that's retention time. Both in LC and GC works the same way, and that's how we identify things. Now, we have a couple of other terms out there that are a little more complicated, and that is the capacity factor and the retention factor. So retention time is simply measured in minutes. Capacity factor, retention factor, both the same. It's both the same thing, both two different words for the same thing. And that is how long your analyte has spent on the column relative to the mobile phase. So if you think about it, if I have an HPLC column here, even a nice short column like this, when you make an injection on the top of the column, the molecules just can't appear at the bottom. They must travel through the column at the speed of the mobile phase. So it takes a certain amount of time for the mobile phase to travel through, and anything after that is the amount of time the analyte spent in the stationary phase. So if we look at the ratio of that, it's called the capacity factor or retention factor, we're looking at essentially the amount of time in the stationary phase relative to the amount of time in the mobile phase. If you think back to PChem, back to physical chemistry, we talked about partition coefficient. So this essentially establishes that chromatography works based on real physical chemical principles, and that is partitioning. Okay, that's sort of deep in the weeds, right? So if we come back out and we say the easy answer, capacity factor or retention factor, we want it to be between 1 and 5. That is the magical answer. I have a cup of coffee here. What do you need to do to that before you could stick it in the instrument? So I have a couple of suggestions for that answer. The first thing is in the GC. The GC can analyze anything that's volatile. Anything that we can vaporize is going to blow right through a GC and cause no harm and no damage. So in GC, I would prefer the entire sample was volatile. the sample, the solvent, the matrix. If everything's volatile, GC is easy. If something's in the sample that's not volatile, like you got blood, which has proteins and sugars and salts in it, then we have to think about removing the non-volatile part of the matrix. Use something like headspace GC. So in GC, the fundamental rule is everything must be volatile in order to inject it. If not, we're going to have to deal with that residue. In HPLC, we have a very similar rule, and HPLC is that the sample must be soluble in the mobile phase. So if my mobile phase is methanol water, I can take any sample that is soluble in methanol water and simply inject it in the HPLC. But one piece of advice, I prefer that you filter every sample in HPLC before you inject it. So whatever the sample is, I like to put it through a 0.2 micron or a 0.1 micron filter, just a syringe filter. I like to filter it directly into the autosampler vial and then cap the vial. By doing that, your columns will last forever. Well, maybe not forever, but they're going to last a lot longer, because one of the major reasons columns die is because particulates accumulate on the head of the column. Those particulates come from the sample. So as a minimum in HPLC, I say filter the sample. When I run Coca-Cola samples or coffee samples, I simply filter them through a syringe filter and inject them directly on the LC. People ask about, oh, aren't you worried about the contaminants and hurting the column? But think about this. Everything in coffee, everything in Coca-Cola is water soluble. How do I know that? Because it's in water. In HPLC, water soluble stuff just comes right off at the beginning. So in the LC world, filter everything. If you're going to dilute the sample, I prefer you dilute it in the mobile phase. So if your mobile phase is 50-50 methanol water, dilute the sample in 50-50 methanol water. That is the best sample prep advice. In the GC world, just make sure everything's volatile, or if it's not, then make sure you get ready to deal with the residue that's going to be left behind. I would say that in the GC, there's one area that comprises the vast majority of all the problems, and that's the inlet. Because in the inlet, we've got a lot of stuff going on. The sample's vaporizing, the helium enters, the split leaves, the column enters. So in all these little spots, we could have leaks, we could have adsorption, we could have different things going on. So my first piece of advice for preventative maintenance on a GC, change out all the parts of the inlet. They're not very expensive, they're supposed to be changed out, so change the liner, change the gold seal, change the O-ring on the top of the liner, change the septum, because we always change the septum, and cut off the top 4 inches of the column. If you do that, you will solve 80% of all GC problems, because those problems revolve around the inlet. So that's my easy answer for maintenance if someone asks you what preventative maintenance you should do on a GC. And the LC, I treat a little differently in terms of mechanical stability. So the first statement is the vast majority of maintenance on the GC is the inlet. In LC, it's the pump. That is where we're going to do most of the maintenance. But if you take care of the instrument, you shouldn't have to do a whole lot of maintenance. So my question in LC first is, how do I know I need to do maintenance? So we look at what's called the pressure ripple, and it's a short-term fluctuation in pressure. If we look at that, that should be less than 2% of the absolute pressure. That tells me the pump is working properly, because things that go wrong with the pump, leaky pump seal, leaky check valve, a bad fitting, all those will result in a pressure fluctuation. So if your pressure is fluctuating, then we go look for a problem, most likely air bubble in the pump. If we don't have any fluctuation, then we say, hey, my pump is working well. One added part to that answer is, if you're working in a pharmaceutical company, you're working with a lot of HPLCs, and in that world, you probably want to do preventive maintenance every 6 months, and you want to, I call this muscle flexing, you want to prove the FDA that you care so much about quality that you're willing to spend extra money to make sure you don't have a problem, which is a good place to be. So I would, every 6 months, change your pump seals, change the filters in your water bottle and your methanol bottle, and some people will go in and clean the detector cell. I usually find that that's not necessary, but commonly in the preventive maintenance procedures, they'll do that as well. It's take a syringe with nitric acid and dilute nitric acid and squirt it through the flow cell. So that would be my answer on preventive maintenance on the LC and the GC. GC, it's simple, it's all in the inlet. LC, it's probably in the pump, but we're not going to take apart the pump unless we have to. So one easy question for the interviewer to ask you is, when you're doing GC, what's the difference between isothermal and temperature program? Well, isothermal, by definition, means one temperature. We're running one column temperature throughout the entire run. Temperature programming means we're going to start at a low temperature and we're going to program to a higher temperature. We always go up in temperature, we never go down. So we give it initial temperature, we give it a rate of, let's say, 20 degrees a minute, and a final temperature. In HPLC, analogous situation. Remember, everything in GC has the same analogous situation in LC. In LC, we use terms isocratic and gradient. So isocratic means one solvent strength. We're going to run 15% acetonitrile through the entire run, whereas a gradient means we're going to start with a weak solvent and program to a strong solvent. We always go weak to strong. So in the reverse phase world, we're going to go from 10% to 100% acetonitrile in, let's say, 15 minutes. So there's your definitions, and that's a low-hanging fruit. You should know those when you're going into your interview. So let's say the job description you're looking at includes lab manager or some sort of management responsibility. One of the things you're going to be asked about is safety. Safety is number one priority. So I think about GC, of course we're going to think about the normal things like we should be wearing safety glasses in the lab, and that especially if we're cutting columns or working with liquids. It's a good idea to never wear open-toed shoes in laboratories. You don't spill anything on your feet. You want to wear a lab coat. So there's the logical things, the obvious things, but specific things to GC. The most dangerous thing about the GC is not the instrument, but it's the tank of gas you have sitting in the back room. So it depends on how they're running the instruments, but historically we'd have 3 tanks of gas for each GC. We have helium for carrier gas, we have hydrogen for fuel, and we have air for oxidant. Those tanks, those pressurized tanks, they're 2,500 PSI. Those are essentially they're bombs waiting to go off. If you were to break the lid, break the top, break the neck off of one of those bottles, we've all heard the stories, it go through walls. If it breaks the hydrogen cylinder, we have a major explosion problem. So although the chances of that happening are very small, we don't hear, there's a million GCs in the world, we don't hear about GCs blowing up all the time, so clearly they make these tanks really strong, but to me, that is my, the place that I focus on in safety, because you want to make sure they're chained up, they're kept properly. Talk about a falling hazard, or you drop one of those on your foot, you break a foot. So my big thing in my lab is I've really tried to get away from cylinders. So we've gone to an air generator, zero air generator. It works off a compressor, so we don't have to worry about pulling bottles in and out. We've gone to a hydrogen generator. In fact, I've got one sitting here right next to me. We love the hydrogen generator. Pour water in the back and get pure hydrogen out the front, and there's no storage and no high pressure issues. I've got one hydrogen generator that generates fuel to all 12 GCs. So easy to work with, easy to get rid of that set of dangers. So that's would be my thing that I would focus on in the GC lab. Now in the LC world, we worry about the solvents. We're using acetonitrile, we're using methanol. They're both poisonous. Methanol, if you drink it, causes blindness, then causes death. So don't drink the bubble phase in the HPLC lab. But we do think about where we store the solvents. I'm still a big fan of carrying around the solvent bottles in a big rubber bucket to prevent us breaking a gallon jug. In terms of the fumes getting into the lab, I think there's sort of mixed views on this. From the one perspective, you'd say the solvents really don't evaporate. Methanol, even though it's volatile, what it tends to do is it refluxes, so it will evaporate up to the top of the bottle, form little droplets, and come back down. So we get, in my opinion, we get very little vapor coming out of the bottles. But if you want to deal with that, especially on your waste containers, there are some systems out there, little carbon filters that you put on the outlets. I happen to have a few of them up here. And that little thing right there is a little vapor cartridge, and what it does is it captures the organic compounds that are coming off the bottle itself. Most labs I've worked in do not use those, but it's something easy that you can do, especially on the waste containers. Consider doing that. I find that most labs ventilation is so, there's so many turnovers in the air that we're not going to notice that. I have a very sensitive sense of smell, and I am hard pressed to ever smell methanol or acetonitrile in our lab. So those are the safety precautions. Again, in LC, you're going to wear your safety glasses when you're around the instruments, because you do get splashing. And I will say, it's happened to me when I was in graduate school. I'm working with an HPLC doing gel permeation chromatography, methylene chloride mobile phase, wonderful mobile phase, great, fantastic stuff, except for the fact that the little piece of plastic tube, when I was putting it, I was taking it out of the waste container, it flicked right into my eye. I was not wearing safety glasses, and ow, it really hurt. So didn't lose the eye, wash it out. But I'm pretty careful about safety glasses ever since then. So those are my tips on how to answer the question, what would you do, what would you look at from a safety perspective in a chromatography laboratory. Now, for those of you who are interviewing in the pharmaceutical industry, there's a couple of special terms that you should be aware of when you go in for that interview. One is the idea of system suitability. So if the interviewer asks you, what is system suitability? The simple definition is essentially it's a way to prove that your instrument is suitable for its analysis, for its intended purpose. So typically what you would do is you would have a standard and you would run it before you run your sample, and if all the parameters check out, then that then says, okay, the system is now ready to accept the samples. If you want to look at more detail on system suitability, you should check out our Axion Lite, where I'll go into a little deeper dive. So another keen area to focus on if you're looking to interview in the pharmaceutical or biotech industry is the idea of method validation. So let me give you sort of a big picture concept here. And that is, in the pharmaceutical industry, you sort of have two parts of the business. You have what I call drug discovery, and there you're developing methods from scratch. There is no outline. You are developing methods for brand new molecules that have never existed before in new matrices. So you're changing the method all the time. The other part of the pharmaceutical industry is the quality control part, and that is you have a method that's locked in stone. It's called good laboratory practice, GLP. It sounds cute, but it means a lot more. It has a very big legal definition. So if you have a pharmaceutical facility that is manufacturing, it's called CGMP, good manufacturing practice. Underneath that, if you have a laboratory working there, you must have GLP, good laboratory practice, which means you have a method. And that method, you cannot change one single thing. You cannot change temperature by 1 degree. You can't make any changes because the method has gone through validation. So the question, what is validation? Validation says, I have a method that works, but instead of just saying it worked once, I'm going to test that method under every possible scenario. So validation may take 6 months, may require $500,000 worth of resources to do for a single method. And essentially the way I describe it is you need to break the method in every which way and see how far you get before it breaks. For example, you have a standard. And how often do you need to make standards? Well, let's run a standard today and tomorrow and a week from tomorrow, left at room temperature. And then a week later and a month later, 2 months later. And then let's age a sample, and we can aggressively age a sample by putting it through heat treatment and that sort of thing. So you will establish, you'll say, the standards must be made up within 2 weeks, otherwise they're no longer valid. And then you'll find where the temperature is too high or too low for the column, or where the flow rate is too high or too low. So essentially, you find every place where the method no longer works, and now you have proof that it works within this regime, within this set of parameters. So method validation takes on a whole a big meaning in the pharmaceutical industry, but essentially it means once the method has been validated, then you can make no changes to it. You'll see something similar in ISO certified organizations. So if your organization is ISO 9001, it means that the laboratory itself is operating under ISO conditions. So you will have validated methods, and you will have method SOPs that you will have to follow. Also in the environmental world. So that is an explanation of validation. How do you know what question the interviewer is going to ask you? Now, we're never sure of what they're going to ask, but here's a clue. Look at the job description, what words they use. If they say something like GC maintenance experience required, then you better study up on the components of the GC. If they ask something like HPLC method development as part of the job, then you really want to brush up on the HPLC method development stuff, not only the components, but the method development procedure itself. The good news is all that's available to you over in Axion Lite. We have in-depth versions of all this, but this is how you're going to know which part to brush up on. Read the job description, look for clues, look for certain words that'll tell you what part of the instrument or what the interview is really looking to find out. Now let's talk about some of the answers that you should not give. And let me explain where I'm coming to from that. If you're coming in and you're claiming that you have experience, please be honest. So if you say, oh yeah, I've worked with HPLC before, then know the details. Know the make and model of the number of the instrument you've been working with. Know its quirks. Know something about that, gosh, the adjuvant stack is really tall if you have that extra detector on there. So details give the interviewer some confidence that you really do know what you're talking about. I think it's really important because let me share a story with you. I interviewed this young person, and they were finishing their PhD in chromatography. Specifically, they were doing GC mass spec of environmental contaminants. So I could see a lot of cool things there. Someone getting their PhD on working with a GC mass spec to do this. So I asked the first question, and just really out of curiosity, it's like, wow, you spent a lot of time doing GC mass spec. What instrument did you use? And there was a pause, and she said, you know, I really don't remember the model number. And that is the biggest red flag. To me, the interview is over. Because if you claim to be, you know, an instrument jockey, you're getting your PhD, you should be living with that instrument. You're with that instrument 24 hours a day. You should know not only make model, but you should know revision numbers. And it's like, oh, this is a Series B, and so it has this adapter, not the Series A. You should be that intimate in the details of your instrument if you claim to be an expert in chromatography. So be honest. You know, if you don't have experience, you know, that's the toughest thing. I see job postings all the time, and experience necessary. Well, where do you get experience in chromatography? You know, you probably took a class maybe as an undergraduate, but in real life, you probably didn't get to touch the instrument. So if you have a chance to volunteer at a college or a community college, if someone has an HPLC or GC, volunteer to work on a project to get some real hands-on experience, because that's what the employers are looking for. Have you touched an instrument? Are you comfortable doing calibrations and making injections? The other great piece of advice I can give you is here at Axion Labs, we teach a 5-day class, and it's hands-on. We do 10 laboratories. You take the GCs apart, you take the LCs apart, and in that time, you get enough hands-on experience where employers have counted that alone as hands-on. And the reality is, it really is hands-on, because by the end of the week, you'll feel comfortable walking up to any GC or any LC, starting it up, choosing the conditions, doing a 4-point calibration, doing an internal standard or external standard calibration. That should become sort of secondhand to you, and it could be if you come here to the Axion classes. So look for some hands-on experience wherever you can. Do the volunteering if you could find it, and let's get you that first great job.